Hello everyone and welcome to Singularity One-on-One. Singularity One-on-One is a feature of Singularity weblog where you can go and listen to it or download it in full. As you may already know, my name is Nicola, aka Socrates, and as always, I will be the man with the questions. Today, I'm privileged to have Dr. Stephen Wolfram as my guest with the answers. Dr. Wolfram was born in London and educated in Eton, Oxford, and Caltech, where at the age of 20 he was the youngest PhD graduate in theoretical physics. He is a distinguished scientist, inventor, author, and business leader. He is also the creator of Mathematica, the author of A New Kind of Science, the creator of Wolfram Alpha, and the founder and CEO of Wolfram Research. Hello, Dr. Wolfram, and welcome to Singularity One-on-One. It is great to have you on our show today.
Hi there.
Hi, so I know that your time is very precious, and therefore I'll jump straight into our interview with the following question. Stephen, can you tell us a little bit more about yourself and your background, but especially why and how you got interested in issues such as physics, cosmology, computation, mathematics, and computer science?
Gosh. Well, some of that is so far in my past that it's shrouded in mystery. I think I first got interested in science when I was probably 6 or 7 years old, and that was in the 1960s and so on. And the space program was big, and that was the sort of exciting technology of the day. And I sort of quickly went from being interested in those kinds of practical technology things to asking what was the sort of foundation underneath it, and got led to physics from that. Then from physics, I got interested in how to work some things out in physics that weren't kind of pencil and paper workable out, and so that got me interested in, well, gee, can I just use a computer to work this out? At the time, the first computer I used, probably 1973 now, was this thing that was, a bit bigger than a big desk and used paper tape and all those kinds of things, and I tried to use it to try and simulate some processes in physics that would be sort of analogous to the second law of thermodynamics, the apparent randomization of processes in nature. As it turned out, I almost wrote a program which would have led me to discover all sorts of things that later I did in New Kind of Science and so on. Almost a very interesting two-dimensional cellular automaton, but unfortunately at the age of 12 or 13 or whatever, the program I wrote wasn't quite the one that would have led me to discover those things. It was something slightly different that didn't have all that interesting behavior. But after that, I was interested in a lot in kind of how structure arises in the universe, how one goes from, for example, having sort of the Big Bang at the beginning of the universe to having all the kind of complex things that exist in our universe today, and that got me interested in things about cosmology. It got me interested in questions about generally how complex stuff gets built in systems. Then, I was interested in very practical, I shouldn't say practical, I should say practical theoretical physics, in working out things about particle physics and figuring out what would happen in particle physics experiments and things of that kind. And that's an area where one has to do a lot of mathematical computation, something that I, as a human, was not outstandingly good at. And so I thought, how can I extend beyond just what I can do with myself, and I realized, gosh, I can use a computer to help me a lot in doing these kinds of computations, and that got me into kind of something that sort of using computers as a tool to do things like mathematical computations, and started building computer languages to do that and so on. And one of the kind of meta discoveries that I made from that is that when you sort of build a computer language, what you're interested in is to take sort of this big mass of complicated computations people might want to do and kind of drill down from that to figure out what are the sort of underlying primitives from which all of that can be built up. And I had done that with some success with computer languages, And I thought to myself, maybe I can do that same kind of thing when I think about the natural world, of going from all this complicated stuff that we see in nature, sort of drilling down and finding out what the underlying primitives might be. And that led me to start studying these things called cellular automata, which are just very simple computational systems, and finding out that even though the programs are sort of almost trivial to write down, the behavior that they give can be extremely complicated. And what I then realized was, this seems like it's kind of the secret that nature is using to make all this complicated stuff that we see around us. It's that when we construct programs, we sort of tend to, at least traditionally, have tended to carefully create those programs to have behavior that we can readily foresee, whereas nature just sort of picks programs, let's say at random or whatever else, and the programs do what they do. And sort of the big science discovery ends up being that if you look at the sort of the universe of all possible programs, that many of those programs, which might not be ones that we would pick for engineering right now, but many of those programs, if you just let them run and do their thing, behave in incredibly complicated ways that are very much like what nature seems to use. So that was kind of a big discovery for me as I started doing these computer experiments now, close to 25 years ago, that led me to sort of ask just how well can one sort of use this kind of computational paradigm to understand lots of questions that have existed in science and technology and other places for a long time. And that led me into all sorts of adventures, among them the decade or so that I spent writing the book, A New Kind of Science, and, well, not just writing the book, but figuring out what to say in the book, I suppose. And the other sort of branch of those things has been the creation of Mathematica and the development of Mathematica, where sort of the notion is, what are all those sort of useful algorithms that have been developed, and how can we take the kind of things that can be computed in a sort of formal way and make them as automatic as possible, so that for the humans, one just has to say, I want to solve an equation, or I want to make some plot of some network or something, and then to sort of have the maximal level of automation in the system, to have sort of the fanciest algorithms sort of automatically selected to behave in the best possible way. So that's been a big project and the obsession of a few hundred people at our company to sort of make Mathematica all that it can be over the last 23 years now. Then the other sort of big strand, I suppose, in my life and times has been what's ended up being Wolfram Alpha, and that kind of came from an interest that I had, from as long ago as I can remember, in sort of organizing knowledge and so on. And I actually recently found some kind of a directory of physics that I wrote when I was 12 years old, and it's kind of depressing and invigorating to see how similar some of the things that I was doing there of sort of organizing knowledge end up being to what we now do in Wolfram Alpha. It's kind of fun, there's tables of data and so on in my little 12-year-old creation. And so when I found it, I'm typing in pieces of these tables and finding out, yep, we can do that now in Wolfram Alpha. That's good. Or in some cases we haven't.
Let me stop you here just for a moment. I'm very interested in what you do with Wolfram Alpha, but I want to just dig a little deeper in Mathematica and in your monumental work, A New Kind of Science, and ask you, what is the ultimate goal behind those? Is it to sort of create the universal equation, or as your talk at TED was titled, to compute life, the universe, and everything?
Well,
is that a fair assessment?
Well, I don't know. I didn't make up that title. So New Kind of Science, NKS, it's often called by people, and Mathematica are rather different kinds of things. Mathematica, the goal is to provide sort of a practical computational infrastructure to do sort of all kinds of formal investigations and to build things like, for example, Wolfram Alpha, which is to most people, it's this computational knowledge engine that responds to questions they ask. To us at the company, for example, it's 15 million lines of Mathematica code, and that's what it is from a sort of software engineering point of view. And Mathematica, the goal is to make possible both the creation of technological things like Wolfram Alpha, and also the scientific investigation. I mean, it's kind of like folks like Galileo had the fun of getting to sort of start exploring the astronomical universe by having kind of the an optical telescope and so on. I kind of see in these years we sort of have the fun of getting to explore the computational universe, and Mathematica is kind of the primary telescope that I've ended up using to do that. So in terms of new kind of science, the real sort of, I suppose the core of it is this idea of exploring the computational universe. We think about, if we have theories about how nature works, we might imagine that nature operates according to some definite kinds of rules. And for the last 300 years, kind of the raw material from which we set up the rules that we discuss as a foundation for nature, that raw material has been sort of the traditional ideas of mathematics. Mm-hmm. People say, let's find an equation that describes this or that aspect of particle physics or cosmology or whatever else, or biology for that matter. That approach has been very successful in particular cases, but there's a vast area of natural world and other kinds of systems that have not been well explored in that way. And so sort of the foundational question that I started off asking was, if we're going to have definite rules for systems, what's the right sort of primitive language? What's the right raw material from which to build up those rules? Mm-hmm. And what I started thinking about was, if we imagine just looking at the universe of all possible programs, what happens when we just imagine that the systems we study are governed by programs that sort of are just out there in this space of all possible programs? And you might have thought that if you have an incredibly simple program, something that's half a line of Mathematica code long or something, that the program's really simple. It must just do very simple things. That's certainly what I thought. Well, I don't know, 30 years ago now. Mm-hmm. And the big surprise was when you actually do the experiment, that's not what you see at all. Indeed, there are simple programs that just do simple things, but there are also very simple programs that do incredibly complicated things. And so what's the significance of that? It tells one, I was mentioning something about sort of the secret that exists in secrets that nature uses to build things, whether it's in biology and making all the complicated forms we see in biology, mm-hmm. Whether it's in physics, making all sorts of things that we know about and in some cases have been quite mysterious in physics, whether it's in informing things about mathematics and sort of how we should think about kind of the foundations of mathematics and the question of sort of what mathematics has been studied versus what mathematics is out there. One of the sort of places where one can kind of drill down and ask what's going on is in fundamental physics, and sort of there's been this, at different times in history, people have been optimistic or pessimistic about whether the end of physics is in sight, so to speak, whether we're close to actually knowing ultimately kind of how our universe is made and being able to sort of get to the bottom of the processes that go on in physics. Right now, I would say we're probably not, in terms of most people's view of this, we're not in a state of high optimism. It seems like the deeper we drill, the smaller the physical scale of processes that we look at, the more elaborate the kind of mathematical structures and so on that seem to be relevant. And it seems like the deeper we drill, it's just going to get more and more complicated. Well, I think that's probably not the case. I think there's a kind of one's intuition changes when one sort of explored this computational universe of possible programs. And sort of the big question then is, if we look at this computational universe of possible programs, is our physical universe out there among these possible programs? So in other words, is it the case that there is a simple program that exists in this computational universe that happens to be the program for our universe? Now, I don't know. That's not a question that one can. That's not really a question of physics. That's some kind of question of, if anything, it's not even quite metaphysics. It's kind of it's a question that we don't really have a basis for knowing an answer to. What we do know is that if we look at our universe, it's sort of a very fundamental fact about it that our universe is not as complicated as it could be. There are maybe 10 to the 100 particles in our universe. It could be that every one of those 10 to the 100 particles is doing its own thing, that there are different rules for each of those particles. We know that isn't the case. We see a lot more order in the universe than that. That's a sort of a basic thing that theologians a couple of thousand years ago were pointing out, that that there's order in this universe. That's a very fundamental fact about it. So then the question is, does that is it in fact the case that the rules for the universe, the program for the universe, is it 4 lines long? Is it 1,000 lines long? 1,000,000 lines long? How big, how complicated is it? We don't know yet. But what I realized is that it's perfectly I've been interested in, well, what would those rules be like? And how should we try to search for those rules? Is it conceivable? If the rules are simple enough, then just by enumerating possible rules, there's a good chance that we'll find the rules for the universe just by enumeration. We don't know that they're simple enough to find that way. We don't know whether sort of Copernicanism is alive and well in the rules for our universe, and whether our universe is sort of special in a non-Copernican way in having sort of very simple rules, or whether our universe is just sort of a typical possible universe out there with rules that are potentially incredibly long and not findable by doing a search. But it's been sort of my, I suppose, hobby for a number of years to explore kind of what's possible, and to sort of explore this computational universe of possible physical universes. And actually, the main thing that has come out from that, it's a sort of a big effort, because every time you look at a candidate sort of universe, you basically have to recapitulate the history of physics to investigate whether this candidate universe that you're looking at is something that could correspond to our physical universe. And I suppose that's a difficult process, because you run into this phenomenon I call computational irreducibility, that basically as you run one of these candidate universes, it takes a certain amount of sort of computational effort for it to figure out what it's going to do, and it seems to be a sort of a theoretically impossible thing to kind of jump ahead in a systematic way to say, well, okay, it took our physical universe, a quintillion steps to get to something that we can recognize. It's going to take our computational universe at the same time, and there's no way to kind of jump ahead and see what the outcome is without following all the steps. So it's been so this is kind of the challenge there, and it's something I've been sort of surprised actually that even I had thought I would have to kind of go through 1 trillion universes before I found universes that weren't obviously not our universe, but actually you start finding things whose behavior is complicated enough that it's very hard to analyze, even within the first, let's say, 1,000 candidate universes. So for all I know, right on one of the servers that we're using for this stuff is our physical universe represented in this computational form. We just don't know it yet, because we haven't been able to figure out the consequences of the particular rules used for that computational universe well enough to know if they correspond to our physical universe.
Let me jump in here for a second, just and change the spotlight and on you just for a second, and see how you fit yourself within that universe. I mean, you have such a wide spectrum of disciplines that you pursue, and the question then is, who is Stephen Wolfram? I mean, do you see yourself as a mathematician, a computer scientist, a physicist, a cosmologist?
Well, I don't know. Anybody who writes a big book called A New Kind of Science probably views themselves as a new kind of scientist. I think, actually, I suppose the categories are a bit broader than the ones you just mentioned, because, I make my living running a company, and I make a lot of what I do is kind of not only the sort of content for science and content for technology, but also the strategy for those kinds of things.
So are you a business person then, foremost?
I don't know. If I'm a business person, well, I've had a fairly successful company for 25 years, so I suppose at some level I'm a business person. I'm the CEO of a company. So if that qualifies me as a business person, then I suppose I am. My sort of internal mindset, I would say, is I like creating things and figuring things out, and I found that the best vehicle that I have for that is a fairly large R&D oriented company, and so I get to figure out a certain amount that's kind of basic science and so on, and a certain amount that's applying that basic science to technological kinds of things. And I think what's actually right now, for example, I'm definitely in a technology phase. I mean, what sort of happened? You talk about the sort of the computational universe of possible programs and so on. Right now, because of all the technology we've built, we're in this kind of strange state where we've got this sort of the universe of all possible products, so to speak. And it's clear that kind of I think it's always you build a certain amount of stuff, and in a sense, it's both. I find it very invigorating to kind of actually deliver that stuff in a practical way to the world, not just because it's nice to get a warm, fuzzy feeling that people are actually finding what you do useful, but also, in my experience, you kind of end up sort of stretching and getting a bunch of new ideas by actually going through the practicality of delivering things to the in some way or another to the world. I mean, for example, right? Yeah, go ahead.
Speaking of the practical implications of your work, I mean, Google considers itself to be an artificial intelligence company, and the question then is Wolfram Alpha an artificial intelligence? Why or why not? And what is Wolfram Alpha?
Gosh, well, I don't know. I'm surprised you say that. I thought I knew the Google folks, and I'm surprised by the moniker "an artificial intelligence company." But anyway, that's
you are.
That's cool. I'm well, whatever. In terms of what, well, so first of all, what is Wolfram Alpha? Well, sort of the foundation of it is a really ambitious project to try and sort of take the world's knowledge and make it computable. Kind of the notion is there's a certain amount of kind of systematic data in the world. There's a certain amount of methods and models and algorithms and so on that have been developed in the course of doing science and engineering and financial analysis, whatever else. There's all sorts of new sort of real-time data that flow in at any given time. And the question is, can you sort of take all this stuff and put it in a form where it can be computed from, and in particular in a form where, for example, if you choose to ask a question that could be answered on the basis of knowledge that exists in our civilization, that you can automate answering that question. It's kind of an extension of kind of the mathematical idea with sort of formal computation, which is sort of to automate things as much as possible so that the humans get to say what they want to do and the computer gets to automatically fill in the rest. And I think with Wolfram Alpha, what we're trying to do is sort of take all this knowledge, make it computable, get it to the point where if there was an expert somewhere, if there could be a human expert somewhere who could work out the answer to this question, then our system can automatically sort of immediately give you sort of an expert level answer to that question. Now, as a practical matter, there are one of the big components to this is sort of how do you communicate with the humans? How do you understand what the humans are asking you? How do you deliver something to the humans that they can readily absorb from? And so, a big piece of it is the kind of understanding human natural language, because that's the sort of richest medium that we as humans have to easily communicate sort of broad ranges of ideas. And on the other side, sort of automating the process of delivering sort of visual and other presentations of information and sort of picking out what information is likely to be absorbable and relevant to a human. So this is kind of the project, at the practical level. It's, racks of servers and, millions of requests going back and forth every day, and all sorts of, 200 people working on kind of sort of the core framework of the system, and lots of volunteers and other people outside. It's a big complicated real thing in the world, so to speak, that happily seems to be growing very nicely. And it's like many of these projects, it's a very long-term project where it's kind of we were just adding up the current to-do list, actually, and at the rate that we are dispatching it, it's currently looking to be about a 20-year to-do list. I think actually our rate of dispatching it will probably increase by a big factor, so that number will go down for the current to-do list. But I guess I'm a person who ends up trying to do these. What I'm most interested in is building sort of large-scale, long-term things, and I kind of like. My sort of favorite way of thinking about it is I really like to build what I call alien artifacts, which means things that once built you can see, well, that's an interesting thing, hopefully, but things which nobody would necessarily think one would build, things which are sort of perhaps at a particular time, for example, with Wolfram Alpha, it's a thing where I'd been kind of thinking about it for probably 30 years. And kind of wondering when was going to be the time in history when it was going to be feasible to actually build such a thing. And I kind of wasn't sure this was that time, but we kind of started it, and it became clear as we went forward that yes, you could really do a pretty decent job of this right now. But that's something that sort of was made possible by this whole stack of technology and science and so on that I'd spent, 20-something years developing. I mean, I think one of the things that's been interesting from new kind of science is kind of the technological implications. I mean, there's this idea of go out into the computational universe and see all these programs and kind of match them up with what happens in nature. But the other thing you can do with all these programs is go and essentially mine them for technology. So, for example, if we look at the algorithms that we use in Mathematica today, also algorithms in Wolfram Alpha, many of them come from essentially just mining this computational universe, effectively just noticing that there's a program out there in the computational universe that does some particular thing that is useful for some purpose of doing some mathematical computation, or doing some image processing thing, or doing something with linguistic processing, or whatever else. It's kind of an analog to what's happened in technology in general, which is, technology typically, we look at the natural world and we say, okay, we know about these materials in the natural world. Maybe they're magnets, maybe they're ferrofluids, maybe they're who knows what. They're things that sort of exist in the natural world and we might have studied in the natural world. And then we get to think, how can we match this up with some task, some sort of human task that we want to do? And that's sort of how we turn nature into technology. We kind of harness what's out there in nature for our technological goals, and that's what we can also do in the computational universe, to just kind of mine the things that are in the technological in the computational universe, and use them for particular pieces of technology. And that's been a sort of a key ingredient in making possible what we've done in Wolfram Alpha and so on. So that's kind of you asked me.
Wolfram Alpha is truly amazing in terms of its capabilities and its potential, and also the way one interacts with it. So therefore, let's go back to the question: is that simply an advanced form of sophisticated computation, or is it going beyond that into the field, maybe early field of artificial intelligence?
Well, I think it's funny when we talk about intelligence. And I've thought about intelligence from a sort of scientific point of view quite a bit. Mm-hmm. The real issue is sort of, can we actually define it? What does it mean?
Yeah.
When is it the case that Wolfram Alpha is like an artificial intelligence, or is it, quotes, just doing computation, right? Does that distinction really even mean anything? And I think the place you have to look to understand this, there's kind of an analog that I think is useful in understanding this question, which is to think about life. When we think about creating artificial life, what do we mean by that? what is the definition of life that we can make it artificial, so to speak? And if you look at history, people have had these different definitions of life at different times in history where they tried to abstract away from what we know about living systems to some sort of essential feature that would be the key discriminant of living versus non-living. And so the Greeks said it was, if it can move itself, then it must be alive. And then people invented steam engines and so on. And then in the 20th century, people would sometimes say, well, if it can reproduce itself, then it must be alive. And then we have all sorts of computer worms and who knows what else that happily reproduce themselves, even though most people wouldn't consider them, quotes, ordinarily alive. But the reason that we can actually meaningfully talk about living versus non-living systems, it's a historical definition. All the actual forms of life that we know right now are all descended from a common ancestor. And so they all share, cell membranes and RNA and God knows what else. So, there isn't really an abstract definition of life that is abstracted away from all of that history. And I think the same is really true of intelligence. And the one thing that we can say sort of as a threshold is that if it isn't capable of doing, for example, universal computation, if it's not computationally sophisticated, then it's not going to be intelligent. But then when we ask, well, what does it mean to say that something is intelligent or not? And we get this question when we're trying to define extraterrestrial intelligence as well. We get this question as a sort of a very kind of everyday thing. People make statements like, the weather has a mind of its own. It seems like the weather is doing things that are sophisticated, unpredictable enough that they are mind-like. They're kind of, and in fact, one of the things that has come out of a new kind of science is this idea, the principle of computational equivalence, which is sort of this way of comparing sort of the computational abilities of different kinds of systems, whether those systems are systems in nature, whether they're systems like brains, whether they're technological systems we build, whether they're sort of abstract systems like mathematics, those kinds of things. And the big implication of this principle of computational equivalence is that actually all those systems are ultimately equivalent in their computational sophistication. We might have thought that, for example, our brains would be just vastly more sophisticated than some simple cellular automaton program that we can write down. But it seems that isn't true. Now, principle of computational equivalence is not something that we can prove. It's something for which we can get evidence. It's something for which there are particular aspects of it that can be proved. We don't absolutely know it's true, but from all the evidence that I've got, it seems to be true. And it seems to tell us that there's no real distinction between sort of once something reaches some threshold of sophisticated computation, it's going to be equivalent in its computational ability. One's not going to be able to say, well, that thing is just vastly more computationally sophisticated than that one. And so, when we look at, so that kind of gives us an interesting perspective, I think, on sort of intelligence, nature, the future even, and also artificial intelligence. And I think one of the things that I've kind of realized is that when we talk about intelligence and we talk about it in our human context, we again, just like with life, really end up retreating to what is essentially a historical definition of intelligence. Is sort of something that's like human intelligence, that's like the way human society is developed, that's like the kind of knowledge base that humans happen to have, and so on. And I think what ends up happening is that the thing that is sort of the Turing test type artificial intelligence thing ends up being something that is defined very much with respect to human experiences and very much the human condition kind of thing. So then you can ask the question, when we build something like Wolfram Alpha that has vastly more knowledge than any human has, and can answer all kinds of questions that there probably is some human somewhere who can answer this question, maybe in some cases not, but it's sort of a collective set of knowledge that really goes a lot beyond what typical humans can do. We can ask the question, is this like an artificial intelligence? Well, it's not very human-like. In terms of, when we do some, let's say, mathematical computation, we work out an integral, for example. It's sort of interesting what we end up having to do. We can figure out that integral in milliseconds with, all sorts of fancy algorithms and all sorts of things that are, bizarrely non-human. But then for reasonably simple integrals, there's a high demand for humans to say, well, how could I do that myself? And then we have to go back from the answer and try and give a sequence of steps that a human could use. We have to sort of reverse engineer for human purposes and say, how could a human do this? And it's sort of interesting that that's kind of the second step. We're able to just go out and do it, but then we have to kind of say, well, here's how you'd feed it to a human mind, so to speak. And it's the same kind of thing. If you look at the way Wolfram Alpha works, it's very, we're just trying to get a result. We're not saying let's reason our way to the result in analog, as an analogy to how a human would do it. I mean, there have been efforts in sort of from earlier phases in artificial intelligence research and so on. It's been kind of let's create a big system that knows a lot about the world and can reason about things. But in a sense, it's kind of an unfair competition because let's say, one's trying to figure out the answer to some physics problem. Well, one way to do that is to do it just like a physics student would do it and try and reason through, or an elementary physics student would do it. Say that, let's reason through that if we push here, then it pushes this up and it pulls down this, and so the answer is such and such. That's approach number one. That's sort of a traditional kind of human intelligence thinking type approach. Approach number two is let's figure out the equations that we can set up, just like people did, figured out how to do in the 1700s or whatever, and let's just blast through the answer and work it out exactly what it is. And that's what we're doing in Wolfram Alpha. Now, it's very non-human-like, intelligence-like behavior. So, if you ask the question, are we creating something that has what one might abstractly call intelligence? I'm going to say I don't think there is something that's abstractly intelligence that is much beyond just this idea of sophisticated computation. What we're doing in Wolfram Alpha, when we look at our own intelligence, so to speak, it's all wound up with the whole detailed history, details of human condition, things like that. The notion of a purely abstract intelligence, I think, is a rather it's a rather desiccated notion. It's something that, and that's interesting, sort of in terms of thinking about the future, because as we imagine sort of where we're going to be able to go in the future, as we are able to sort of outsource more and more of our thinking-like activities to computers and so on, and as we are able to build sort of more and more sophisticated computers that can emulate sort of every aspect of what humans might be proud of doing, whether it's proud of doing math or proud of recognizing images or proud of solving word puzzles or proud of understanding natural language, whatever else, we're going to be able to do all of those things, and many of them quite soon.
So can we even speak about the concept of the technological singularity at all then? I mean, given all you just said, what are the implications of that on your perspective on the singularity as a viable sort of potentiality for our future?
I think the future's going to be, I think, more different from the past than one might, than many people might imagine. I mean, I think that one of the things that will be true, probably, is that we will have gotten to the point we'll be able to optimize everything. And so for example, if we start thinking about the technology that we have explored so far, and this kind of computational universe is a good framework in which to think about the space of all possible technologies. Usually we just say, well, we've got technology, we develop technology, this, company does this, it's kind of like a natural selection type thing, some technologies win, some lose, et cetera, et cetera, et cetera. But we can kind of think of it in a much more efficient way than natural selection. We can think, what's the space of all possible technologies? It's kind of like the space of all possible programs. And we can say then, what have we explored so far? What's out there to explore that we haven't explored so far? And I think one of the first things one realizes, what we've explored so far is tiny. And it's very wound up with a lot of history of engineering and so on. I mean, we look at circular motion and levers and who knows what else in mechanical systems. We're looking at these very simple, very regular kinds of behaviors that those are the programs in effect that we've explored in traditional engineering and traditional technology. what we've learnt is that, well, first of all, nature goes beyond what we've done. That's why nature seems to make stuff that's so much more complicated than the artifacts we tend to have right now. But even beyond nature, nature is only exploring some tiny part of this computational universe of all possibilities. But we could, if we wanted to, imagine a technology where we explore anything that's out there. And so there's a lot of, for example, the technology we have today where when you're shown an object, one of the ways you can guess that it's an artifact is just seeing it looks a lot simpler than the stuff that nature tends to make. But the other way you can guess is that there's a lot of historical aspects to it. It's got circles, it's got other things that are easy to manufacture, these kinds of things whose operation is sort of functionally understood by people and so on. I think that sort of in the future we will be able to have things that are much more sort of created in a way that whose operation is much more better optimized, because the programs, the systems that are created by sort of traditional engineering are often optimized for creatability. They're not optimized for their functionality. When you optimize for functionality by just sort of searching the space of all possible programs, you often end up with these things that look a lot more nature-like and a lot more complicated. So the thing that we'll see is a lot of what we as humans do, it will start to be sort of outsourced to devices. We've already seen that. The operation of those devices will look a lot less and less human understandable. More and more of it will be kind of found programs that just exist in the computational universe, turn out to match some particular human purpose, so we use them. And then what I think will happen is that a lot of what we currently see as being things where, that's just impossible, you can't do that, it will turn out we figure out the physics, we figure out the computation abilities to be able to do those things. And I think the big challenge for the future is not what's possible, but what do you choose to do. And so there will come a time when our sort of thinking like processes are well encapsulated in digital form. There will be things that we can do there, with Wolfram or whatever else, that are just vastly more than we as humans have ever been able to do. But the real question is, we can sort of do anything. What do we choose to do? And that gets us into the whole question of, people might say, well, all these programs out there in the computational universe, they may be nice and fun and make nice pictures and so on, but what are they for? What purpose do they serve? And this is where we kind of get into something where it's sort of an important problem for thinking about the future, I think, is understanding purposes, understanding human purpose, understanding the evolution of human purpose. Because I think more than technology, which I think will get to the point where sort of in some sense we can do anything, the question of human purpose is going to much more determine what's the direction that we see things going in. Because, right now, it's sort of interesting to watch the evolution of purpose. A lot of it is historical. Almost inevitably, it's historical. That the things we think are worth doing now are because that was something that kind of arose from the history of our civilization, and different, prongs of civilization or whatever have identified different purposes. Purposes we have today in, sort of modern Western society or something can be vastly different from purposes which people have had at other times in history and so on. And I think, one of the questions is, as we look to the era in which, in a sense, anything is possible, how do we figure out what is worth doing? What we should, what direction should we be going in? Because at some level, I think sort of the bad view of the future of history is more or less this, that we take our sort of processes of human thinking or whatever else, we can sort of commit them to highly optimized, molecular scale sort of physical computational processes, and then at the end of it we've got all these electrons going around in some elaborate pattern, and that was in some sense can be interpreted as the elaborate sort of future thoughts, future sort of computational actions of humans. But when we look at this thing, it's something that has all these processes going on, but we can also look at a rock, which also has all these processes going on, all these electrons going, whizzing around. And this principle of computational equivalence tells us that actually there's nothing less sophisticated probably about what happens in lots of kinds of rocks than there is in this funny creature that's been created by this sort of ultimate future projection of human technology. And so then we'd say, well, what's special about the one that's the future of humanity as opposed to the one that's just the rock? And the answer, I think, is not something which we will be able to abstractly say. We won't be able to say, oh, look, there's an emotion running around there, or oh, look, there's a some kind of general intelligence factor or something that exists there. There will be no such distinction. The distinction will be something about history, and the distinction will be that's the thing that encapsulates somehow the particulars of it. Isn't a question of the general computation that we're achieving. It's a question of the particulars of human history and so on that we have. That will be the thing that's special about what it is that sort of is the successor of us in the future. And I think, for example, in Wolfram Alpha, one of the things that's sort of interesting is that one of the things we're trying to do is really to encapsulate a lot of what civilization has achieved with respect to knowledge. It isn't something, in Mathematica, some part of what we're doing is to have this very pure, precise sort of, this is what's possible computationally. We're also trying to capture a fair amount of formal knowledge, but it's kind of one thing is sort of saying, one of the things that's interesting with Wolfram Alpha is just this capturing of what it is that sort of is the essence of kind of what we've achieved as a civilization, what we've achieved sort of from the point of view of systematic knowledge and so on.
So in that sense, do you think we should be optimistic or pessimistic about our future? Because I mean, can we even speak about that in terms of our sort of historical perspective of the changes that are about to come? And I mean, some people are sort of fearing the future, the radical changes that you've mentioned. Other people, such as Ray Kurzweil, most famously, are very optimistic and often criticized for being overtly too optimistic.
I think it all relates to purpose, right? It's all a question of we'll be able to do almost anything. And then, that means that many purposes can be achieved. Whether you feel this question about optimism and pessimism is kind of almost a derivative of this question of how do you think about purpose? Because it's hard to be optimistic or pessimistic if you don't know what the purpose is. Now, from the point of view of it's kind of always fun. It's like with extraterrestrial.
From evolutionary point of view, maybe one would say a Darwinist might say the purpose is survival. Right. So therefore, if you believe that humanity will not survive, therefore you're a pessimist. And if you believe it would survive and thrive, maybe in a new form or shape or level, then you'd be an optimist.
Well, fair enough. I mean, in that sense, I would be extremely surprised to see it not survive in some form. Mm-hmm. I think that's the question of somebody from today might look at the future form and say, my gosh, all these things that we struggled with, whether it's finite lifespan, or whether it's having to deal with the awkwardness of biological existence, or whether it's lack of immediate access to any knowledge or whatever else, all these things we struggle with, they're all gone, and isn't that wonderful? And then they might say, but this is very boring. What's the point anymore? And, that might be the view from today. The view from the future, this sense of, how purpose will evolve is, I think, it might be that everybody, that people operate in a way that, they can feel that they have, a purpose that's wonderfully achieved for that time. I think that one of the things I think sometimes is sort of amusing is it may be that sometime in the future, as I'm saying, this thing about what's possible, what computations can be done, and so on. A lot of what will happen there, I think, is people will say, well, anything's possible, right? So then they'll get very interested in, well, what should we do? What purpose should we have? Right? And how do we find a grounding for our purpose? Whether it's, at any given time in history, there are different groundings. Maybe it comes from religion. Maybe it comes from something about the way society operates. all these different things. Maybe it comes from very sort of physiological, sort of pleasure, purposes and so on. There are these different purposes, and one of the things that sort of amuses me at some level is that if people or the descendants of what we are today, so to speak, are saying, well, what should the purpose be? They may look back to the history of the human condition, so to speak, and ask, well, what did people think the purpose was way back? What did they think the purpose was in the first decade of the 21st century or something? Maybe that's what we should be. Well, yes. But I think they. But one of the things that's interesting about today is that for the first time in history, a ton of what's happening today is precisely recorded. Mm-hmm. And if you go and ask about the time of Socrates in ancient Athens, right? We have only probably only a couple of megabytes of information about what went on then, whereas today we're beginning to have just a gusher of information about what's actually going on that will be preserved into the future. And it's sort of one of the amusing possibilities, I suppose, amusing from the point of view of our responsibility today, is maybe the things we're doing today will sort of define the future, will define purpose in the future, because it will sort of be the thing that gets studied as a even if we don't know what the purpose is today. I mean, it's a little bit like you see in lots of kinds of traditions where you say, well, we don't really know why we're doing it today. This is some ritual that's been passed down for thousands of years and has sort of developed a purpose almost by virtue of having been passed down for thousands of years.
We only have about a minute or two, so let me just ask you one final question before we call our interview to an end. And that would be, if you have one message that you would like to give to our listeners today, what would that be?
Oh my. I suppose that's a complicated thing. There are many things to say about the world, and I think.
Can you not reduce it down to a single sentence?
Well, I don't know. It's I've been spending some part of my life trying to reduce what the universe does down to a small program. I'm not sure that. Look, I think if the question is sort of what can we expect in the future, and what can we perhaps do today as we think about that future, one of the things that I suppose I think we have now from new kind of science and so on. We have kind of a framework for thinking about these things, sort of a new framework for thinking about these things that sort of is in a sense ahistorical. Traditionally, in most fields of kind of human inquiry, we have ended up taking what amounts to a very historical point of view, even in mathematics, for example, where one might think that's a formal abstract area where people get to sort of just investigate all that's possible in kind of in abstract systems of rules. That's not actually how mathematics has been practiced. It's been very much something where people started from kind of what was known in ancient Babylon, thought about in ancient Babylon, and have kind of progressively, incrementally generalized from that. I think the thing that is kind of most interesting, so it's kind of a historically driven field, and that's been true with most areas of human inquiry. I think the thing that's really interesting about sort of the computational universe right now is that we get to actually explore it ahistorically. We get to just sort of explore it as a kind of a very basic science thing. And I don't know the implications. I've explored only certain swaths of the computational universe. There's a lot more to explore, and I suspect that if we want to understand the future and what's possible in the future, that sort of understanding this kind of, in a sense, it's the most basic science. It's pre-science in some sense of what's possible out there in the sort of computational universe of all possible systems. That's kind of the place to study. And if we look at the trajectory that we'll follow in the future, we can kind of explore, we can kind of map out in this computational universe, okay, in the the history of humanity up till the 21st century, explored this little corner over here, and we're now getting to kind of make bigger forays out into this computational universe. And I think that the one of the things that sort of is our best hope to have sort of a systematic framework to understand what's possible is this kind of investigation of the computational universe. So if there's so it's a good thing to do. I've spent some part of my life doing it. I would like to spend more of my life doing it. I think at this point I'm kind of in a sense polishing some of the technology that's made possible by exploring this computational universe. But there's a lot more out there to explore, and I think it's something that's pretty important for our future to do that.
Dr. Stephen Wolfram, it was a pleasure having you on our show today. Thank you very much.
Thanks.